оказывается А с чертой какого-то странного индикатора. Вы могли просто сказать, пусть y в x над k это накрытие ГЛУА, и y геометрически связан.
Да.
И работает правильно.
Но нет, тогда, значит, что утверждается? Вот, например, допустим, какое вот, собственно, утверждение нам предстоит доказать. Вот у нас есть гладкая собственная схема, ну, для простоты обозначений, над ZP. Значит, у нас есть накрытие, конечное накрытие ее общего слоя, который над купе.
У нас вот здесь накрытие от купе с чертой.
Ну, после замены базы оно будет определено каким-то конечным расширением купе с чертой, поэтому я могу сделать замену базы и считать прямо над купе. Ну, над конечным расширением купе. Хорошо. Вот по существу нам надо доказать такое утверждение. У нас есть гладкая собственная схема над локальным полем, скажем, над купе. У общего слоя есть, значит, какое-то накрытие ГЛУА с группой ГЛУА, у которой порядок взаимно прост с P. Тогда, значит, после конечного расширения купе, возможно, разветвленного, это накрытие продолжается до накрытия вот всей схемы над кольцом целых этого конечного неразветвленного расширения. Вот что нам надо доказать. К бесконечным неосерым расширениям переходить не надо.
Если мы докажем вот только над самим купе, если у нас есть накрытие...
А это неверно просто. Ну, потому что, ну как, вот, например, у спектра купе есть накрытие, а именно можно присоединить корень квадратный из P. Вот получится неразветвленное накрытие спектра купе. Конечно же, оно не продолжается до неразветвленного накрытия спектра ZP. Но оно продолжается тавтологическим образом. Да? Значит, вот все, что мы хотим доказать, да, что давайте я это сейчас пока напишу. Значит, мы будем доказывать такое утверждение, что вот, значит, у нас есть x, вот это вот спектром тут у нас есть спектр k, здесь есть спектр k маленькое, значит, и есть какое-то накрытие y, которое мне надо k обозначить над x, значит, это будет накрытие ГЛУА, и его группа ГЛУА, ее порядок взаимно прост с полем, с характеристикой поля вычетов, тогда существует конечное расширение, такое, что значит, если я сделаю замену базы, то вот это отображение продолжается где B это целое замыкание. Значит, вот это то, что мы хотим доказывать. Без этого, конечно, просто вот совершенно неверно, даже если x это само спектра.
Если многообразие x имеет хорошую редукцию к модулю p, то y имеет потенциально хорошую редукцию.
типа того. Okay, so that's so here is kind of our ultimate goal to prove this result. So, well, kind of putting it in a very broad terms. So we have a cover, finite étale cover of an open subscheme of a scheme, and we want to kind of see when it can be extended to the entire scheme, possibly after a base change. So this is our ultimate goal. And so last time we set up kind of a tool for doing this. So we proved the following. So last time we observed that so we have x was integral Noetherian and the most important condition, normal. Then so we have the category of finite étale covers over X. And on the other hand, yeah, so maybe I will recall some notation. So we have the function field of X, the field of rational functions, and I denote it by capital K. Do not confuse it with the notation there. So so this is the spectrum of this guy is the generic point of X, and then we have the restriction functor that takes a finite étale cover over X and restricts it to the generic point. So finite étale covers of spec K, right? And what we observed is that this functor is fully faithful. So the functor, again, takes y over x to y times spec k over x over spec k, base change, restriction. So, so we proved this by showing that if x is normal, then any finite étale cover of X can be recovered from its generic fiber as the normalization. So this is normalization. So if I call this spec L of X in L. So, so if I have any finite extension of this separable extension of this field, or more generally, disjoint, well, the product of, well, any separable finite dimensional algebra, it's just the product of finite separable extensions. So disjoint union of points, not one point. Then I can construct, I can take its normalization, which will give me a finite cover. It need not be étale and it need not be flat. But the construction still, well, still I can, the construction of normalization works in general. So, so as a corollary from this fully faithfulness, we observe that we have surjection on fundamental groups. So we have the fundamental group of generic point, spec K, which is nothing else but the Galois group of K bar over K. And by functoriality, it maps to the fundamental group of X. The claim is that this map is surjective, that this is the quotient of the Galois group of the function field. For example, the fundamental group of spec Z is the quotient of the fundamental group of Q bar over Q. And what is the fundamental group of spec Z, by the way? So we are looking at finite extensions of spec Q such that its normalization of Z in this finite extension, so the ring of algebraic integers in this finite extension, is a tal over Z, so nowhere ramified. It's a non-trivial result of Minkowski is that there are no such extensions, that fundamental group of spec Z is actually trivial. It's a very nice corollary of Minkowski lemma on convex bodies. So it uses some real math. So in this case, I'm saying that it's not a very precise information. It doesn't tell us much about the kernel. And what we really want to understand now is what can we say about the kernel. So putting this more geometrically, so again, assuming the X is normal, we see that if we have a finite Étale cover over an open subset of X, then there is at most one way to extend it to a finite Étale cover over X, as the normalization. You can take first restriction, the generic point, and then take the normalization. So, sort of the goal of this lecture will be to develop some technique for study abstractions to extending a finite Étale cover over a punctured, well, over an open subset of a scheme to a finite Étale cover over X. So we are going to study ramification. That's the goal. So, and here is the first result, which is really, it's a deep result by itself. And this is a theorem of, unfortunately, I don't, well, it's attributed to Nagata and Zariski. So, well, I guess at least they proved it in the affine situation, and which is not a big difference. So the result is the following. Suppose let X be a regular connected scheme. Connected scheme. Okay? And suppose I have a finite morphism. So in particular, X is normal. And suppose I have a finite morphism, F, which is a normalization of X in a finite separable extension. Of the function field. K function field of X. Okay? So again, so we want to see, we want to kind of understand under what conditions this F is Étale. So the theorem asserts that assume that there exists an open subset of X of codimension of the complement So x minus u in z in x greater or equal than 2. And that restriction of f inverse of u to u is étal. Then f is étal. Okay? So, for example, so let's derive a corollary from this right away. So, the same assumptions on x. So x is regular if codimension of x in x minus u is greater or equal than 2, then the embedding by 1 étal of u into x induces an isomorphism on fundamental groups. So, so here is kind of a basic example. So suppose you have a surface over some field, smooth surface. A is a point. Then the map from x minus a induces an isomorphism on fundamental groups. Okay? That's so of a fundamental group of a punctured surface is the same as the fundamental group of x. So there are no. So if u has the complement to u has sufficiently large codimension greater than 1, then there are no obstructions to extending a finite étal cover over u to a finite étal cover over x. This will be used for.
Does it fail for non-smooth surfaces?
It does. It does. So how you prove it for over complex numbers? So in particular, suppose that k is c. Then we could try to prove this result by comparing it with just usual fundamental group, and then I claim that the result follows from the following fact that just usual fundamental group of C n minus 0 is equal to 0, well, provided that n is greater than 1. So here is your surface, and here is a point A. So suppose we want to we want to prove that removing this something of codimension, real codimension 4, right, does not change the fundamental group. In fact, for smooth real manifolds, it's enough to assume that the closed subset you remove has codimension what? Codimension 3. It doesn't change the fundamental group.
Yes, but this holds without smoothness.
Well, how?
You can introduce a CV structure on C points such that this point is a vertex. And if in a CV complex you remove something for dimension 4, it still doesn't change the fundamental group, right?
So really, I'm not so. Well, I don't think that this is enough. So you don't you have to construct a CW structure such that you don't have extra distance. So let's see. Well, first of all, this is not compact. So how you I'm not quite follow what you say.
If you have any algebraic set in R.
Как бы в том, что все равно же у нас отображение компактной окружности, оно попадет.
Нет, но у нас же не окружность совершенно. То есть вопрос какой? Вот мы берем какое-то очень особое многообразие, берем. Ну нет, тут точно это, конечно, неверно. Если вы просто рассмотрите гиперповерхность. Ну, это, наверное, верно, но мне кажется, что там топология просто будет другая. То есть сейчас я попробую привести конкретный пример, когда это совершенно неверно. Значит, что, собственно, о чем речь? О том, как устроена топология проколотой окрестности, точки на негладкой поверхности. Я утверждаю, значит, в случае гладкой поверхности проколотая окрестность топологически гомотопна сфере, правда? И поэтому, значит, если сфера имеет большую размерность, то вот. А я утверждаю, что в негладком случае там может быть абсолютно все, что угодно. Может быть, значит, да просто конус надо взять. Давайте возьмем конус над эллиптической кривой. Вот, возьмите эллиптическую кривую и возьмите конус над ней. Что будет, если вы выбросите вот эту точку и рассмотрите проколотую окрестность? Как будет устроена фундаментальная группа? Вот эта вот проколотая окрестность, она будет отображаться на эллиптическую кривую. Это будет расслоение со слоем С со звездочкой. Чему равна фундаментальная группа? Ну, в общем, посмотрим. Надо дальше воспользоваться точной последовательностью фундаментальных групп для рассвоения и увидеть, что фундаментальная группа этой проколотой окрестности, там просто фундаментальная группа базы этой эллиптической кривой появится. Хорошо?
Да, нет, хорошо, конечно. Я просто к тому, что Степан сослался на теорему про C-W комплекса. Она правильная, но мне не очевидно, почему на проколотой окрестности есть вообще структура.
А вот здесь есть? Ну, я не очень знаю, как там с собой. Сейчас. Разве на любом аналитическом множестве есть структура C-W комплекса? Я подозреваю, что здесь тоже есть, по крайней мере, в этом примере. Но очевидно, что фундаментальные группы другие. Хорошо? Okay. So, well, to derive this assertion from this one, well, one way to do it is to use one-camping theorem, right? So if you have a topological space which is covered by two connected open subsets, and such that the intersection is connected, then the fundamental group of the topological space is free product of the fundamental groups. Well, it's co-limit. So if X is U1 union U2, then pi1 of X is co-limit in the category of groups of the following diagram. Pi1 of U1 intersected U2, pi 1 of U1, and pi 1 of U2. Right? So you have this, this diagram. So what is called limit? It's a group with the following universal property: to give a homomorphism from this group to anything is the same as giving a pair of homomorphisms from this, such that the compositions are equal. So you sort of, it's okay. So the idea is that you look at the entire surface, write it as a union of the complement to a disk and the disk, and so write down this colimit in this case, and then you remove one point and write similar diagram. So the diagrams are going to be actually the same. Okay. So we want, if we we want to have an analog of this. So this computation proves the result in the case when case. So we want to prove it over a finite field, over a field of characteristics. Well, for schemes, not in characteristic 0. Okay. So good. Let's see what I want to is probably this. So this is itself is a very useful result and has kind of we will use it not only in the proof of this specialization theorem that here. So okay, so let's discuss a proof. So let's start with an easy part. So so this is proof of this Zariski-Nagata theorem. So step 1. So let's simplify our life. Let's assume an addition that f is flat. And let's prove. So we show that in this case, give a simple argument that f is etal. So this will be a proof of Nagata-Zariski theorem under an extra assumption, which is in fact very unpleasant, but still it will be used in the proof in general. So okay, so what we have to show? So let's consider direct image of the structure sheaf. And by flatness, we know that this is a vector bundle, and this is an algebra object in the category of vector bundles. It's also an algebra.
F star OY.
OY, thank you. So this is a vector bundle. Да, потому что это когерентный пучок, так как морфизм конечный. Значит, если я знаю, что он еще плоский, но конечно порожденный модуль над локальным неотеровым кольцом, если он плоский, то он свободный. Полеми Накаямы. Good. So now what? So this A has an extra structure. It's we have the trace form. Trace form, which maps to X. This is Q of X comma Y is equal to trace of X times Y, right? So there is a trace homomorphism from functions on Y to functions on X. Good. So, and the condition that a flat morphism is a tull is equivalent to saying that this form is non-degenerate. So, want Q. Well, I will say that okay, non-degenerate. I have to explain what it means. Meaning that it induces an isomorphism. So if you have a form on a vector bundle, it gives a morphism. I can think of this as a morphism from A to the dual vector bundle, right? And so we say that it's non-degenerate if this is an isomorphism. So it's non-degenerate restricted to each fiber of the vector bundle. Да, это единственное. Зачем где я этим пользуюсь, чтобы след определить. Как я определяю след? Я сначала определяю его для общих точек, получаю рациональную функцию, а потом она след, как сумма собственных значений, еще и целая алгебраическая. Поэтому, да. Okay, so we have this non-degenerate. Okay, so that's what you want to prove. Well, in order to prove this, we may assume that because this is a local statement, right? We have a globally defined map. We want to show that it's an isomorphism. It's a local statement. We may assume that A is trivial as a vector bundle. And let H be the determinant of the gram matrix. Matrix of Q. Well, if you have a trivial bundle, then just choose a basis and write this Q in this basis. You get a matrix with coefficients and functions. So the determinant, so this H is a function on X. So what does it mean for a form to be non-degenerate in terms of H? When a form, bilinear form on a vector space is non-degenerate. How looking at the gram matrix to see whether it's degenerate or not? It must be non-degenerate matrix, right? So that means that the determinant must be non-zero. So
if characteristic is 2, then what do we have to do?
It doesn't matter. So we are talking about bilinear forms, not symmetric forms, not quadratic forms. It has nothing to do with characteristic.
Kind of, I mean, on a one-dimensional space over a field of characteristic 2,
Yes?
you don't have bilinear forms then.
What do you mean? Why?
You don't have symmetric bilinear forms because they have to be, because all symmetric forms are
So the Gram matrix is just the matrix of this operator.
Его невыраженность на любом поле проверяется ненулевым детерминантом.
Okay. So what we want to see is that h is an invertible function. But we know that h restricted to u is here. And we also know that codimension of x minus u is greater or equal than 2. And the zero locus of a function cannot be, well, if zero locus has codimension greater than 2, then that means that the function is non-vanishing by Krull principle ideal theory. So this implies that h is here. Okay, so this completes the proof of the Zariski-Nagata theorem under this extra assumption, which is really so. Okay, so now step 2. So let's assume that dimension of x is equal to 2. Case when dimension is 1, there is nothing to prove, because u must be everything then. And we want to show flatness. F is flat. Okay? So how to check flatness? So we may replace let me see. So I want to so I want to show flatness, or equivalently that A is a vector bond. Now, so replace x by spec. That's a local statement. So yeah, so I have u, and I have x, and I have here I have a finite collection of points, which is x minus u, and I assume that I need to show flatness at every point of the complement. So this is a local assertion, so you can replace x by localization. So I have this A. This is a coherent sheaf. This is a finitely generated module over this local ring. And I know that its restriction to the complement, to the maximal ideal here. So here I have maximal ideal. And I know that, sorry, this is maximal. And I know that if I restricted A to the punctured spectrum, then it will be a vector bundle. And I want to show that A itself is a vector bundle. Okay. So this is, in fact, this is automatic. Почему? Ну, значит, вот я хочу доказать, что вот это, что А определенное как прямой образ, это векторное рассвоение. Я знаю, что это векторное рассвоение в ограничении на U, потому что на U все в порядке, я знаю уже этальность, в частности плоскость. То есть у меня вот есть А, это когерентный пучок на поверхности, и он является векторным рассвоением, значит, на дополнение к нескольким точкам. Я хочу доказать, что это тогда векторное рассвоение. Значит, единственное, что мне надо, я буду сейчас использовать, это что, давайте вот это вот отображение обозначим буквой J. So we have this open embedding J. So the only property... Это то, что мы хотим доказать. Значит, вот я хочу доказать, что А — это векторное расслоение на X. Ну, давайте сначала его... Значит, я утверждаю, что достаточно доказать для каждой точки в дополнении, что ограничение этого когерентного пучка сюда будет векторным расслоением. Это нужно доказать. А я уже знаю, что на дополнении к максимальному идеалу, здесь единственная есть замкнутая точка, это векторное расслоение. So the only property that I will need is that A is equal to J rho star of its restriction to U. So in fact, for surfaces, it is true for smooth surfaces, for regular schemes more generally, of dimension 2. It's true that if you have a vector bundle on a punctured scheme and take J rho star of this, then you get a vector bundle. So suppose you have a surface, regular surface, remove a point. So take for U just a surface minus 1 point. Take the trivial, even line bundle, the structure sheaf on U, and take J rho star of that. What do you get? So what is J rho star of something? It's what are sections of this guy? These are sections of so sections of the direct image is the section of this guy over punctured open set, right? By definition. So suppose you have, well, a picture like this. So what are global functions on my x? Sorry, on U. So my x is this, and U is the complement to 1 point. What are global functions on this non-affine scheme?
So any global function extends to there's still
Binormality, right? If that's true for any normal scheme. Singularities of a function are always supported in codimension 2 or higher. So at least, well, this statement would make sense. If A were trivial, then, the general claim that I make is that if you take any vector bundle over a punctured surface, take J rho star of that, then you get a vector bundle. So if you apply this construction to a trivial vector bundle on U, then definitely you get a trivial bundle, right? So, but it doesn't at all prove the assertion. It's not true that I would need to show that every vector bundle on U is trivial. That's equivalent to my assertion. Good. So let's check this. So I'm going to check flatness. So I will check that A, which is, well, I take stock. So that's what we want to check. A is a flat or XA module. So how you check flatness? Well, you want to check that the torus, right? So you have tor over A, I, A A and K, over K is 0 for I greater than 0. In fact, it's enough to check that tor 1 is equal to 0. For modulus over local rings, its flatness is equivalent to this assertion. So you compute this tor by picking a convenient projective or free resolution for K as a module over this. And here we are going to use regularity. So how to write a resolution? Well, you take OXA, that's free module. Then you take OXA x1 plus OXA x2, and then OXA x1 x2. So for regular rings, surfaces, you have what's called the Cazuli resolution. So, and I will substitute this, well, I will use this resolution to compute tor, right? So, so this is, so I will have, so this condition is equivalent to saying that if I take A plus so here the map is multiplication by x2, x1, right? So the first component is multiplication by 2, and here it's maybe minus. And here it's also x1, x2. So it's projection composed with this multiplication. So we want to show that it's acyclic. So this will be positive, this will be degree 0, this will be degree -1, this will be degree -2. So acyclic in negative degrees. So let's observe that, let's rewrite this. So I will consider the following complex, double complex. Here I have multiplication by x1, and here I have multiplication by x2. So this is a double complex, and what is written here is the total complex of that, right? So we want to show that the total complex is acyclic in negative degrees. So okay, so let's consider the following map. So the co-kernel of this map. So I extend this diagram. This is x2. So I'm saying that so the flatness is equivalent to two statements. First of all, this map is injective. And secondly, this map on x1 is injective. Right? So do you agree with the fact that acyclicity of this complex in all degrees, negative degrees, is equivalent to these two assertions? So you see, if you know that this map is injective, that means that this is a short exact sequence. And this is also a short exact sequence. Therefore, my double complex is quasi-isomorphic to this complex. Because the rows, right? Because this map is a quasi-isomorphism. This map is a quasi-isomorphism. So the double complex is quasi-isomorphic to this one. But so in particular, it's so if I know injectivity, then we have that. Да. Ну, значит, это означает, что вот тотальный комплекс вот этого квазиизоморфен тотальному комплексу просто вот такому. Но этот комплекс, он, если я предполагаю, что вот на x2 это вот у меня инъективное отображение, вот x2, то тогда, значит, когомология только в одном месте.
По идее, первое утверждение нам гарантирует инъективность первой стрелки, второе гарантирует точность в среднем череде. Почему последнее сюрьекция?
Well, no, so you agree with the fact that the total complex is quasi-isomorphic to this?
Well, yeah, but then you only require that this has no cohomology in upper degree. But what about lower degree?
But I don't. But this is degree 0. I am not saying that my complex is acyclic. It's acyclic only in negative degrees. It has homology in degree 0.
Because this is degree 0.
Yeah. Okay, good. So now the first assertion is actually obvious because my A is a vector bundle over a punctured disk, right? So it has, if it had sections killed by x1, it would mean that it has sort of sections supported on a divisor, right? And I know that it's not the case. It's a vector bundle over the punctured disk. So the only thing that I need to check is that this second image. So 1 is okay. And 2 is so let's check it. So suppose I have S, which is a section. Right. So and suppose that it's in the kernel. Well, it gives me an element in the kernel. Suppose that x2 s is equal to x1 s prime. So what do you want to check? That that s over x1, okay, maybe I don't even have to write it. Then s over x1. So I want to check that, so s is 0 here, meaning that it's divisible by x1. But I claim that S over x1 is a regular section. Right? So why it's why it's regular. So this is x1 equal to 0. This is x2 equal to 0. So definitely, well, I take a regular section and I divide it by x1. So the only singularities I may have are here, right? So I claim that maybe away from this point, nevertheless, the section is regular. But okay, so I know that if I take this guy and I multiply it by x2, then I get s prime. But x2 on this line is non-zero away from this point. So if I have a rational section that becomes regular after multiplying by an invertible function, is itself regular. Then the section itself is regular. So that's regular on U, and therefore it's regular, S is regular. Why? Because A, I recall that A is JO star of A restricted to U. That means that sections of A on X are the same as sections of A on U. So if I have, that's all. So it seems like it's a short argument. Surprisingly, so what we actually proved here, we proved again that for every coherent sheaf of this form, such that this is a vector bundle, this A itself is a vector bundle. With a little bit more work, you can show that if you have if you start with any vector bundle on U and take JO star of that, then you get a vector bundle. What is the difference between these two statements? So, so you have to show first that JO star of a vector bundle is a coherent sheaf. It's not at all obvious, right? JO star, in general, does not preserve the property of being coherent. If you take a structure sheaf on a punctured line, extend it to take JO star of that, you get functions on this arbitrary pose at one point. But when your point has codimension 2, it might have chance to be true, and that's true. So one can first show that for any vector bundle on U, JO star of that is a coherent sheaf, and then this argument shows that it's a vector. Since I don't need the assertion and that generality, I will not prove it. But, well, this method does not work in dimension 3 and higher. So because you may have non-trivial vector bundles on a punctured neighborhood of a point in dimension 3.
So is this assertion a corollary of our proof, or what is?
What is assertion?
A equals J.
No, it's not a corollary. It's so this is how A was defined as the direct image of functions on Y, and Y is normal, right? It was a normalization of a normal scheme in a separable extension. So Y is normal. Therefore, so we are saying that if we have a function on Y which is regular away from the fiber over this point A, then it's regular everywhere. But this fiber over point A has codimension greater than 1.
Sure. And we use this assumption, this assertion in where?
Yeah. So to get from here to here.
Oh.
Okay. Otherwise, I could take for A, for example, the maximal ideal in the ring of functions in this local ring, in this local ring, right? It's not, yeah, it's coherent, but it's not locally free. Good. So what can you do in general? So, in fact, I don't know how Zariski and Nagata proved this, what did they do. So Grothendieck rewrote essentially all commutative algebra results known at that time. And so his argument uses weak Lefschetz for a fundamental group. So I will explain this. So dimension. And here I will not give a kind of all the details. So dimension of x greater than 3. And here you use induction on dimension of x. And so
as stated, we don't have the dimension of x because Nagata and Zariski knew how to construct Euclidean rings of infinite full dimension, right? Something like that. Could x be a spectrum of such a ring?
for regular rings, okay, so let's see. So we are looking at a point, but maybe it will be too confusing. So you may replace x by a local ring. Yeah. Okay. Now what you do? So in a second, I'm going to do further reduction. So replace x. Well, definitely I can replace x by the spectrum of the local ring, but I claim furthermore that you can replace it by spectrum of the completion. That's completed local ring. So this requires a little bit of work because so if you have a coherent sheaf, then well, a finitely generated module of a local ring, checking flatness is equivalent to checking flatness after completion because the completion is flat. So one has to be either check that this kind of passing to completion commutes with the normalization or use kind of Beauville-Lois's law argument here. So it's, let me just say that it requires some work. So I will assume that I'm in this situation, that we are in a formal disk X is a, okay? So then what do you do? So I want to set up the induction. So I pick H, which is in M modulo M squared. And I want to consider in X the hypersurface cut by equation H equal to 0. It's going to be a smooth hypersurface. So I have X, and I have here spec or X A. That's the self is X, but I want to remove from this. I want to mod it out by H, right? This is a hypersurface, and I will call it X0. So here I have my punctured neighborhood. This is U. And similarly, I have punctured neighborhood here. I remove maximal ideal. Now, okay, so this is these are closed embeddings, and this is open embedding. So let's, and maybe this will be called U0. Okay. So what is fundamental group of pi1 et al. Of X? So X is the spectrum of a complete local ring. And we already discussed that this is just pi1 of the residue field. Spec K. So pi1 of X0, well, that's also a spectrum of a complete local ring. And therefore, its fundamental group is also equal to the same. The embedding of the closed point induces an isomorphism. So that means that you have this commutative diagram. These maps are given by embeddings. So it's commutative. That means that this is an isomorphism. So any the finite total covers of X, the category of finite total covers of X, is equivalent to the category of finite total covers of X0. So now, yeah, maybe let's see. I can erase this. Okay. Here is what you want. You want to show that finite et al. Cover of U extends to X as a finite et al. Cover. You want to show that the fundamental group of a punctured disk is the same as the fundamental group of the residue field, which is so 0 if it's closed, if case, little case closed. So let's contemplate that. Let's look at this diagram here. So we have a finite et al. Cover of U. What can we do? We can, so I want to, sorry, we have finite et al. Cover, of U. So, of U, right. So first thing that I can do, I can restrict it to this U0. So restrict it to U0. Okay. Then, so X0 is also regular, right? Because it's obtained from X by, it's cut from X by one equation, which has non-zero differential. Yeah, it's non-zero. Oh, yeah, it's non-zero. Yeah. So I should. Sorry, I should rather say this. It's better. Okay. So that means that we already know that every cover of U0 can be extended to a cover of X0 by induction assumption. So extend to x0. And then to x. Well, I know that the category of finite total covers of x0 is equivalent to the category of finite total covers of x. So there is only one way to extend it. Okay, so what is written here? This is a recipe for constructing a finite total cover of x starting with a finite total cover of u. The only problem with this recipe is that it's not clear that it gives the right answer. So what do we want? We want to show that, so after all, the restriction, so we get some finite total cover of x, and we want to show that its restriction back to u is the one that we started with. And so what we definitely know is that the restriction of this finite total cover to u0 is the right one. So what we need for this to work is the following fact, that pi1 of u0, so it maps to pi1 of u, that this map is surjective. That so if you have two finite total covers over u, then their restriction to u0, well, then a finite total cover of u is determined by its restriction to u0. So if you have two guys here over u, then their restriction and their restriction to u0 are isomorphic, then the original guys are also isomorphic. That's equivalent to surjectivity. So, okay. Good. So what this statement is equivalent to the following, that if you have for every v over u, this is a finite total cover of u. U0 это, ну вот x0 это гиперповерхность в x. А u0 это та же самая гиперповерхность минус та же минус как бы точка. Угу. То есть вот у меня картинка такая. Вот у меня есть x, вот у меня есть гиперповерхность, и вот есть точка А. И что я хочу доказать? Что, значит, меня интересует, я могу эту точку выбросить, значит, вот это вот у меня u0. А u это все. И вот, значит, утверждается, что отображение вложения из этой проколотой гиперповерхности в проколотое трехмерное многообразие, что оно индуцирует суръекцию на фундаментальных группах. Вот этого будет достаточно. So this is a very concrete statement. So for every finite total cover with connected total space, its restriction, and I need some names, v times u0 over u0, let's call it v0, is connected. So that's kind of surjectivity of this map on the fundamental group is equivalent to this very concrete statement about covers, right? So what does it mean? So why it's true? So if something is, if a cover is connected, it means that the corresponding set, the action of the fundamental group on the fiber is transitive. So if it's if this map is surjective, then action of even of this group on the same fiber is also transitive, and vice versa. So good. And now here we are going to use some formal geometry. Yes, and now I'm going to use it.
But why don't you just take phi 1 of the generic weight, surjects?
Yeah, but I'm going to use it now. Good. So what do we want to show? So let's take U. Here I have U0. And here I will have UN, which is spectrum of the completed local ring modulo h to the power n plus 1 minus maximal ideal. Right? And here I have U0. So I want to think of U as kind of limit of this infinitesimal thickening, right? So here is my picture. So here is U, and now I take kind of thicker and thicker neighborhoods. And similarly, I have Vn, which is V times Un over U. Okay. So let's. So what do we want to show? So we want to show that if V is connected, then this guy is connected. So assume that it's not connected. Then this Vn are also not connected. So I can construct some idempotence in the recurrent functions on this guy. Just if you have a variety which is scheme which is not connected, you can take a function which is equal to 1 on one connected component and 0 on others. So I can construct some functions here, idempotence. And hopefully I can kind of, because my this ring is complete, so this neighborhood is very small, I can kind of take the limit of this idempotent and get idempotent on V. So it's enough to show, and this is true after all, that global functions on Vn, on V, well, it maps to limit of global functions on Vn, that this map is an isomorphism. Okay? So let's again look at this picture here. So if instead of punctured neighborhoods I have just x, right? Definitely global functions on x, so which is this complete local ring, right, is equal to the limit of these quotients by definition, because this ring is complete. In particular, it's H adically complete. But the problem here is that I take punctured neighborhood, and that may change the, well, it may kind of affect. So, and it's definitely, yeah, say if x had dimension 2, imagine for a second that x has dimension 2. Вот, которое написано. Я хочу сказать, что если я здесь v заменю на накрытие y, например, да, то тогда утверждение будет очевидно. Но почему? Потому что y, ну, okay, so let's let me write here an obvious statement that OX A completed is equal to the limit of OX A modulo H to the n plus 1. But even if I replace x here by functions on x by functions on u, this statement is no longer that obvious. And in fact, it's obviously false if dimension of x is 2. This guy is much larger than this one. So let's consider this picture. So my u, so this is u0 is this punctured neighborhood, right? What are functions on this punctured neighborhood? So imagine that this is just a two-dimensional, the ring of formal power series, spectrum of the ring of formal power series in x and y over some field k. So then this guy, x0, is given by equation x equal to 0. So this is punctured formal disk is spectrum of the Laurent series in one variable. Right? So what are functions on u in this case? Well, these are well, that's something very, very complicated. No, at least I would have elements like 1 over x plus y over x plus y squared over x plus and so on. That would be an element here, right? And it's definitely not a function on x. It's not a Taylor series. So because, so in dimension 1, what you have, the functions on the punctured neighborhood in dimension 1 do not necessarily extend to functions on the formal disk. So this space could be huge. Okay? So what is the argument here? So, okay, so I have to stop here, and I said that I will not give you, so that this is a true fact. And using some relatively easy search, you reduce it to showing that the same is true for you. And I already explained that this is false when dimension of x is 2. So un or un. Okay? This is a very concrete statement about local rings. And it's still non-trivial. So it's so this is derived from two statements. First of all, from this. And secondly, from vanishing of the first cohomology. Okay? That's a kind of. I don't want to return to this construction, and mostly because a nice kind of really kind of conceptual argument here uses the notion of derived completion that we haven't discussed in this seminar. So the argument is written in Stack's project. It is short once you have some tools from homological algebra.
I still don't understand. Why don't we have pi1 at the tau equals
Uh-huh.
function field on U.
Yes.
We have a corollary that it surjects onto pi1 of u0. By the same corollary, it surjects onto pi1 of u. And we have this map. This commutes has surjected.
Well, are you saying that this statement is obvious?
Yeah, I don't understand. I think we have the corollary that pi1 of the spectrum of the generic point surjects both here and here, and this commutes.
Let's see. No, because U0 has smaller dimension.
Then what?
You don't have this map at all. This is a map from generic point of a scheme to a scheme. And the generic point of this scheme is different.
So it gives us isomorphisms here and here.
Yes.
Vertical.
Yeah. Mm-hmm. Okay. Good. So, questions?
Это текст теоремы Левшица, да, если...
Теорема Левшица. А вот это называется теорема о чистоте. Опуса, да.
Зарисского Нагата.
Да.
Написано в одном журнале.
В смысле, они независимо доказали?
Это две статьи. Сначала Зарисский, потом за ним прям Нагата статья.
В смысле, они и тот, и другой доказали совершенно независимо, одно и то же?
Нет, я боюсь, что Зарисский доказал характеристики 0, а Нагата характеристики P за ним.
Ага.
Они договорились, и было это опубликовано в одном журнале. Но вот это просто я знаю, у меня есть две эти статьи подряд, как бы в одном журнале. Вот, только, ну вот, остальное я не помню.
Понятно. Very good. More questions?
Но сам Зарисский это вроде как-то доказывал с помощью, ну, как бы вот детерминантного критерия, но тоже, да, с определителем. И где-то он вроде тоже использовал пополнение, то есть, как бы, как мне показалось, то есть, как бы, или там формальные ряды, он как-то вот, ну, в смысле, вот, поэтому
Yeah, I have a question.
близкие.
It's not very relevant, but so we have a finite group G.
Mm-hmm.
We can construct an algebraic stack BG such that its objects over a scheme X. The fiber category is precisely what we denote finite total of X, right? Is this correct?
No, these are G torsors. So these are finite. What does it mean? What does it have to do your category with G?
So it's a subcategory here.
It's not a subcategory. It's finite et al. Covers such that G acts on this simply and transitively.
So these are objects here with Galois group G notation, right?
No, it's identified with G, right?
Correct.
Yes.
So is it true that our main theorem is sort of just can be reformulated to say that BG is a proper step, right? This is just the evaluative criteria of properties.
Well, remember that you need to make a base change. You need to pass first to a ramified extension.
Yes.
So, and evaluative criteria, maybe, maybe you, let's see, so, yeah, so you are saying that in evaluative criteria of properness for stacks, you are allowed to, it should be, it's formulated differently. You are allowed to pass to some possibly ramified extensions of your discrete valuation domain.
Yeah, for example.
Probably you're right.
If you have a stack of elliptic curves.
Yeah, you're absolutely right. But I'm not sure that. So here in this Grothendieck theorem about specialization map, we really have some assumptions on smoothness and properness. And so your assertion about the properness of the stack kind of would imply something for any scheme X. And I'm a little bit concerned about this.
So because it looks like at some point in this proof you also use something that would be equivalent to separating. So
Mm-hmm.
Is this not? So this should not match up exactly.
I will think of this. I believe I would rather guess that the answer is no. It's not. Okay. Thank you.